Hi, I'm Krati, and today we're going to talk about building a generative model. If you were with me in the last lecture, we talked about transformer architecture and how the attention mechanism comes into play. And so today would be a good point to maybe talk about how it's coded, because honestly, I feel that if once you see how easy it is to really code the entire decoder only generative model, it takes away all the overwhelming parts of it, and then it's a little easier to maybe talk about GPT versus DeepSeek because you already know you have some background and you already know how that works. And just FYI, we're only building this model to know that it can be done and it's easy. But usually, when you have a task to do, a generative AI task to do, you don't build a model from scratch because it's really resource intensive and languages have huge vocabularies, and there's a ton of good open source models available on Hugging Face, and usually you'll just fine tune that. On that note, so fine tuning in regs and LoRa and all of that good stuff we're going to talk about in the advanced LLMs playlist. But for now, we're only going to build a small model from scratch and stick to the basics. Okay, so what to expect from this presentation exactly? What kind of model are we building? So we'll build a recipes model, like your generative AI model should be able to, given some ingredients, it should be able to generate some recipes for you. And the model's going to be really bad. And there's going to be a ton of gibberish in the model, the output. Why is that? Well, I'm already aware and I know that the model's going to be bad because you need to have a ton of data to make sure that the model works great. And this is just an example, so I didn't put too many resources into it. We just want to build a good or a bad model, something that generates any generative model, something that generates, that's it. And yeah, it did generate a lot of gibberish, but it's okay. It'll going to solve our purpose. But what you are going to learn is how a decoder is implemented, and we're going to experiment with different learning rates to see if there's less gibberish in one model versus the other one. And yes, we're also going to discuss the effect of tokenizer on the output generation for a simple model like the one we're building. So yeah, let's get started. Let's talk a little bit about character level tokenizer. So if you look at the example on the screen, it says what's going on, and if you look at all the tokens that a unique tokens that will be generated from a character level tokenizer, you will see that it's all of the characters and space, and yeah, so it takes all the text you have and it breaks it down into a character, and then we take a unique set of those, and that is what a character level tokenizer basically does. But that's not the only type of tokenizer. There's two other types: word level tokenization, where each word is a different token, and then there's subword tokenizer like BB and WordPiece, and this is the most common types for LLMs really. So yeah, for instance, and this is really cool because it reduces the amount of unknown tokens that are there in the vocabulary. Because let's say that you have a word that's called unhappiness and the model hasn't seen it, but it has seen un and happiness. So yeah, it's pretty cool that it preserves semantic meaning even when it's a subword tokenizer. So then the next question is that if the subword tokenization and the word tokenization, these are so cool and so intuitive, why do we really need a character level tokenizer? Well, there's a couple of reasons. Number one, text generation. For example, GPT-2, it allows more control over letter level structure, and sometimes there's noisy text in general, like it works better for typos and anything short lang or OCR even. And there are some languages without spaces where characters have meanings of their own, like for instance Chinese and Japanese, and tokenizing with words there would be much harder, so character level tokenizer is much easier. And yes, it works well for pronunciation modeling, and yeah, for low resource languages when word level models they need large vocabularies, but the character doesn't, it's just all the characters. So yes, pretty good, it's got a ton of advantages. Okay, Alright, let's talk a little bit about the code now. In the first two sections, I'm only importing the required libraries. The dataset that I'm using is called Recipes for a Better Life, and that's available on Kaggle. By the way, this notebook's also available on Kaggle if you want to check it out or edit it yourself. Okay, so the only pre-processing that I'm doing in this data is I am making in the data frame, I'm adding a new column called text, where I'm taking combining two columns called ingredients and directions, and as a string, and then I'm dropping everything that's not available. So that's the only step I wanted to. There's obviously a ton of pre-processing in real life scenarios, but for the intents and purposes of this video, this should be enough. Right, so the text data frame should look something like this. Okay, now on to the main part of the character level tokenizer. So the first thing that we do is we join the text data frame all together, and then we create a set of it because we only want unique values. And then we turn it into a list and sort it. So that way you have a set of unique characters, and the length of it is basically your vocabulary. So now you have a set of unique characters. The next obvious step seems like we want to make a kind of index for it. So we create the character to index and the index to character mappings using enumerate. These are just two dictionaries. By virtue of it, for each index you can look up a character, and similarly for each character you can look up its integer index value. And you would do that for all the characters in text, and then you would do it for all the text. So this is like a double for loop. So for all the text in the data frame, and inside that, for all the characters inside that text, you create a character to index mapping for each character. And that's about it. That's the character level tokenizer. Okay, now we have our encoded text. After this line, we have our encoded text. So now we create a dataset. For this, we will need a tensor, because this cannot exactly directly go into the decoder. We need it to be a tensor. So we create a custom PyTorch dataset, which has these three methods: the initialization, the length, and the get item. A little bit of refresher on this is the init method can have any parameters that you need, and it's typically used to have it's very variable. It's typically used to set the configuration of the dataset. The length, it doesn't require any parameters, but it will return a dataset size. It must be an integer. And yes, for get item you only need the index, and it returns tensors. So that is how the dataset class works. Okay, so the encoded text is our encoded text that it is taking as input. We created this right here, and the sequence length is the sequence length that the output that will that the dataset will output. So the length is simply returning this length of the encoded text. And now for get item, okay, if you look at it, it's very simple. This is looking at if the length of the text is greater than the sequence length, then you chop it. Like, we want all the sequence length to be of the same size. So if it is greater than your sequence length, then you cut it. If it is smaller than your sequence length, then you add the paddings. And that's basically what this piece of code is doing. In the end, for all of it, you convert it into a tensor, and yep, that's what you return. You return a tensor of input sequence and then target sequence. That's pretty much what the PyTorch dataset class is doing. These are the hyperparameters that we're using for this code, and I will highly recommend that you try different hyperparameters to see what the different outputs are. I did try reducing the learning rate and changing the number of epochs and even the batch sizes, so that's a pretty cool thing to try. it really changes the way the model learns, and it does change the output that it generates. Okay, yep, and here we're just creating the dataset and the data loader. The dataset is the instance of the recipe dataset class. It's taking encoded text and sequence length. And then the data loader has dataset and batch size. And yes, we are shuffling it, so we set that to true. Okay, so for the decoder class, we need two methods, the init and the forward pass. So here, the first thing is to get the nn.module to initialize for proper functioning of it. And then for the embedding, we use the nn.embedding. It takes in vocab size and embedding dimension as parameters. For the positional encoding, it's kind of interesting. Here we're using the, for positional encoding, we're using nn.parameter, making it a learnable parameter, the positional encoding. Let's look at that for a second. Okay, so why are we using nn.parameters and not just the exact position? Like, why not hard-code it? So yeah, nn.parameters make it a learnable information for the model. It allows to learn the optimal positional representations during tracking, and it also provides automatic gradient checking. And also, those are not the only ways to kind of use for parameter encoding. You can also have fixed embeddings, that is sinusoidal, that were used in the original Transformers paper. Attention is all you need. And there's also an option for relative embeddings, which can be useful especially when you have longer sequences. nn.parameter automatically registers the tensor for gradient computation. So we're essentially making tensor full of zeros for it and then updating it using backpropagation later. And this is exactly what the nn.parameter is doing for us. Alright, okay, so that's for nn.parameter. And now we have the decoder layer and the transformer decoder layer. Okay. So what the self.decoder layer is doing is that it's creating one transformer decoder layer using these parameters, and then the transformer decoder is taking all of that layers as a parameter and then building the entire architecture for it. And then this is finally the linear layer with the embedding dimension and the vocab size. Now let's have a look at the forward. And so what exactly is it doing? So X is the input tensor, and its dimensionality is usually batch size, sequence length, and embedding dimension. So we take the second argument and we dynamically adjust the positional encoding to match the sequence length. And this is all that's happening in the first part of the code. If the sequence length is greater than the positional encoding size, then you add positional encoding to match it. Otherwise, if the positional encoding is larger than sequence length, then you truncate positional encoding. And that is all this is doing. So if you dynamically adjust the encoding to match the input sequence length. And for the second part, we have to add the positional encoding to it. So basically self.embedding, what it does is that it converts our tokens into dense vectors of fixed size. And since transformers don't process sequentially, then we need to add the positional encoding for it to know the order of the right words. For the second part, we are using self.transformer decoder, where X is the query and the other X is both key and value. So that way you will have an attention matrix for both of those. And then the last one is a linear function that's like a fully connected linear layer that maps decoder's output to the vocabulary size, and then it returns the tensor. So this is, after all this processing, you finally get the tensor back. So this is exactly what we had learned in the transformer. Let's look at this with a little example, like what happens when this passes through the function. Suppose we have a sentence called the cat sat. And let's, for instance, assume that we are doing a word level tokenization, and for each of the word we have different token IDs. Now we map each of those to a dense vector, with sequence length 3 and embedding dimension 4. So sequence length is 3 and the embedding dimension is 4. And this is what the dense vector X is going to look like after after embedding it. So and then each token is projected into a query key and value using learned weight matrices, and then attention is calculated for one word with each of the other words. So that's what x comma x that in the previous code meant. And then finally you apply attention to values, and the output of the attention is passed through the linear layer. Right, so just a little side note which confused me when I was first learning it, that X here is not a token. What we're passing is a tensor, and a tensor has many tokens, and that's why we're finally able to build this. So, okay, on to the training part of it. So here we are training, we're using the cross entropy loss and atom we're using as an optimizer. If you don't know what these are, I will link some resources down below for you to study these, but that's out of the scope for this lecture. And okay, so for the training loop, for a batch in the data loader, first thing that we do is that we clear the old gradients, and we use it using optimizer.zeroGrad. This is a function that clears the old gradients, and then we do the forward pass, right? That's your output. You compute the loss, so you compare the output and the target, and if it's very different, then the loss will be larger. If it's somewhat closer, then the loss will be lesser, and that's what you compute. And then based on this loss, you do like a partial differentiation and convert and find out the derivatives, and that's the backward step. And then based on this, you update the weights and biases. So this is the optimizer step. Okay. Alright, so what's happening here is that you have a batch that is a small group of samples processed at once. So if you have like 10,000 samples in your data set and batch size is 100, then you have 100 samples per batch. And batch means that only one batch would have 100 samples. So you would do this thing for every batch. You would clear the gradients, forward pass, compute loss, compute new gradients, and then update the weights. This happens for each batch. And then you do that again for the number of epochs. So when you say that, when you say 1 epochs, it would mean that it has seen all of the 100 batches. So if you run it for 3 epochs, then your model has seen 300 batches, and that's how it's done. So yes, there is a forward pass for each batch, and then a backward pass for each batch, and then the loss is average for each epoch basically. Then gradients are cleared, and this process is repeated for the next batch. Note that this doesn't set to random the weights and biases. So the weights and biases are improving with, that's kind of the point, like your gradients, because of your gradients and the backward step, your weights and biases are improving. Okay, and yep, this is what happened. So yeah, finally I'm just printing all of this out and updating the total loss. Of course, that's also a step. Initially you set that to 0, and then you keep updating it. So I tried different hyperparameters to kind of train it, but in the end my loss was 2.4, which is not great, even for a character level tokenizer. This wasn't so great. And finally I'm saving the model, and this is a very simple code just to generate new recipes. Here you run it with torch.nograd because you don't need all the stuff that you needed in training. So that's the output, and then you generate the next character. You generate with the start text, that is basically the input that was provided. So right, when I pass into my model ingredients, flour, sugar, eggs, and milk, and then I ask for directions, I want to see what it generated, and it is absolutely crazy because it generates a lot of gibberish, total nonsense. But the point here is that it did generate something, and because it is character level and it had very little data to train on, I wouldn't expect any better. But yep, this is what the model has learned, and I will definitely encourage you to kind of try it with different hyperparameters. Maybe reduce the learning rate and increase the number of epochs, or change the batch size, and yep, that could give like a different output. Okay, now that we have looked at character level tokenizer, we are going to start with the subword level tokenizer. Up till here, the steps are the same, the data pre-processing remains the same. But here, we initialize a BB tokenizer. Let's look at that for a second. So, what is that? A byte pair encoding tokenizer is a subword algorithm used in NLP, and it is used for training large language models like GPT, and it obviously, as we discussed before, has a lot of advantages. That it handles the out of vocabulary words, it has very good compression, and it is very common for LLMs. Also, a good side note is that for character level models, a good loss range is 1 to 2, but we had our loss at 2.4, so it could tell you that that could be one of the reasons why the output that was generated was not that great. For a subword or word level model, a good loss range is 0.5 to 1.5. So you can remember this when you're trying to use a different tokenizer to try to generate outputs. A byte pair encoding tokenizer versus a character level tokenizer. So if you remember in the previous version, the custom dataset class was a little bit different. Here we have we're training the tokenizer with our data frame, and the init class takes tokenizer text in max length, let just returns length, and here for encoding we have self.encoder.encode, and we are taking the text for all the indices. For input IDs, we are just taking all the IDs up to the max length, and yep, if they are not of the same size, we are padding them with a little bunch of zeros, and in the end we're returning the tensor for input IDs. Okay, then we just initialize the dataset. The decoder is more or less the same. We are still using the cross entropy loss and Adam optimizer. The training is the same. Again, you can try for more epochs, and unfortunately the loss here is still 2.3, and as we said, it has to be something like between 0.5 to 1.5, so yeah. Here, when I'm passing the ingredients, the directions, they look like they make sense, but they really don't. But the good thing is that because our vocabulary is full of semi-words or broken up words, then at least you can make out some words in here. But ideally, if you find a set of hyperparameters that make it work with a limited dataset, then it might just work. But yes, overall, this is how a decoder only transformer works, and it's, if you look at it, it's basically 3 steps, right? First, you pre-process your dataset. Second, you train a tokenizer on the same dataset, and then you write your decoder class. And the steps are same. Like the only variable parameter here is the hyperparameter. So there's number of heads for your attention layer, the number of layers, the feed forward dimension, the embedding dimension, and so on.